0.8. 6. How's it going? Oops. Going? Doing all right? Good, good. Yeah, hold on, crafts, hold on. Emerald, custom, I'm trying to remember my wife's. Yeah, she sells them. Let me see. Yeah, okay, here's her page. So somewhere on here. She makes the cups. Yeah, she makes these things. She does it for fun. She's a PA. She's very busy with work. This is kind of like her outlet that she does just for enjoyment. But these are the flags that I make. So yeah, no, that's wood. How do you do this? Okay, there we go. So there's a thin blue line. How do you switch? Here, yeah. But I don't know what flag that is, actually. Hold on, I don't know which one that is. Yeah, it's some country. I don't know. That's Tennessee. That's a Tennessee flag. That's Puerto Rico, I think. That's India. So you can't tell, but this is all like CNC'd in here. And then that's a cool one. This is American flag that has shells for military people who have the, what are those called? I don't remember what those are called. Yeah, that's just a close-up of like the detail of the work. Yeah, and then I do American ones. Depends. All these stars are like etched or CNC'd in. They have different sizes. Let me see, hold on. That's a small one, yeah. It depends on, the time really just depends on how many I'm making at a time. I like to make them in batches. If I do one at a time, it takes forever. But if I do like 6, it's much better. Because I have to like rip each of these pieces, like rip them down, start with a big piece. Anyways, all right. Oh yeah, there's more Texas ones, yeah. Anyways. All right, well, let's see. We got some People at home here, can you all hear me, see my screen?
Yes, sir.
Yes, okay. Let me just double check my audio here. Yes. All right, I'm just going to do one thing here. Give me just a second. So we're going to, today we're going to do 6.6. It's going to be all solving equations. And then on Wednesday, of course, we're not going to have any face-to-face or Zoom meeting at all, because I'll be in Houston. My wife will be having surgery on Thursday. She's having the pre-op stuff on Wednesday. So I can't guarantee that I could be at a computer. So y'all voted last week, I think, to say you wanted to do it this way. So I'll do a video. I'll send a link to a video. I'm going to keep it short. I'm not going to do an hour, 40-minute video. It's going to be on the next section, which is applications of solving exponential equations. We're going to talk about exponential growth and decay models. So I'll explain how it works, and then I'll do a couple of examples, and then I'll give you some problems to do. And to make it worth your time, I'll make it worth something, okay, that'll be turned in. That way, that'll motivate you to actually do it, all right? All right. Yeah. No, it won't be. I'll give you a day to turn it in. So just to give you just a kind of breakdown on how this is going to work, we're going to Houston. She's having surgery on Thursday. She's going to have drains put in. Okay, so sometimes when you have surgery, you have to have drains to like let fluid and blood and stuff like that out. And they take those drains out at some point. So we've been told the drains can come out anywhere between like 3 to 8 days. It depends on how she handles it. So if it looks like it's going to be like 3 days, we may just stay in Houston and wait till Monday morning to get the drains out. If that's the case, I won't be back on Monday. So please just stay tuned to your email. The plan is, if we do have to stay through Monday, I'll hold a Zoom class, but I won't hold a face-to-face. All right, so I'll Zoom from Houston. Hopefully I'll have decent internet, and we'll see how it goes. But just stay tuned to your email. I would say like by Sunday, I should know, I would think. Okay, we'll see. We're supposed to check out on Saturday, so I might know sooner. Okay, any questions on the next few days, next week? We also have an important date coming up here. We have the drop date for your classes. Any class you want to drop, the 12th, Friday, this Friday, so you can still withdraw. I talked about that already. All right, well, without further ado, we are going to solve equations that involve exponential and logs. So before we start, I want to establish all the properties, all of the things that we need in order to do this. And I'm also going to grab my calculator, because we will need our calculators today. All right, so let's start with, this is kind of a review, but there's also some other stuff on here that's not quite review. So I'm going to just start this with properties of exponentials. Yes,
When it comes to the calculator, should there be a certain brand or
a certain brand or something calculator? No, that's fine. I always say that, if you're going to move on and take more math, if you have to take, pre-cal calculus, maybe Cal 2, eventually you're going to want to invest in a graphing calculator. And in that case, I would say, Texas Instrument is usually the brand most students have. There's Casio also, but Texas Instrument, TI 84 plus is like their flagship, I guess. It's good. You can spend more money for ones that are in color and other things, but there is a certain calculator you don't want to get, which is anything that has what's called a CAS system in it. That stands for Computer Algebra System. This calculator I have right here has it in it. This is the TI 89. I don't even know if they make this anymore. TI 89 titanium, but most new calculators will say CAS on them. you cannot use those on most exams that you take. As you move forward, a lot of professors, and then any standardized test that you ever have to take, they won't let you use a CAS. So it's because it'll do things that you should be doing. Yeah. Yeah. I mean, like these can solve equations like this, that one can solve equations. The basic ones can solve, but these do, the ones I'm talking about, the CAS, they do what's called algebraic manipulations. So it can factor. It can take like x squared minus 4 and turn it into x plus 2 times x minus 2. It can do, and that's just the beginning. It's like there's all sorts of stuff it can do. So there's a huge difference between a CAS and a non-CAS calculator. Most students get the CAS, they don't even know how to use it, so it's not a big deal. But you know, if you do know how to use it, you really have an advantage over your classmates. Okay, so properties of exponentials. We'll start with that. So we're just going to go back and just remember some of the things we're going to need today. First thing is that if you have, let's say, a raised to the x times a raised to the y, that you can put those together by adding the exponents, right? That's a property. And then if you do a raised to the x and then you raise all of that to the y, then you multiply the exponents. This all look familiar so far? Yeah. Okay, those properties we'll need. And then this one is a little bit odd, but I think we are definitely going to use it today. It's oops, I forgot to put, if a to the x equals a to the y. So if you say that something raised to the x is equal to the same thing raised to the y, then guaranteed the x has to be y. We actually talked about this property last class also. When we were trying to solve some exponential equations, we said, hey, if you have the same number, I'll just give you an example on the side here. If I say 4 to the x must equal 4 to the third, well, since these have the same base, I can guarantee that these have to be equal. X would have to be equal to 3 here. But I told you, you can't, oh, this isn't always true for other types of equations. I think I gave you the example of like x squared or something. So those are the main properties for exponential functions that we're going to need. The properties of logs, let's do those next. Oh, you know what? There's a few others I want to put here, just so we have them. We should all know that a to the 0 is 1, right? We all know that any number to the 0 is 1. And then, of course, you know, a to the 1 is a. Those are kind of, I think most of y'all understand that. I just want to put it up here just so we have it. Okay, so properties of logs. All right. And I think it might be worth it for us to number all these properties so that when I use them later, I can say, hey, just go look at that property 6 or something. So let's call this property 1, 2, 3, 4, and 5. Okay. And then for logarithms, I'm going to continue the numbering. So I'm going to say 6 just so we can refer back to it. Okay, the first property of logs that we need to know, log base a of 1 equals 0. We talked about that last class. And this is because if you try and do that loop, a to the 0 would equal 1. Right? Remember that little loop, a to the 0 equals 1. The seventh property, log base a of a, would be 1 because a raised to the first power is a. The next property is log base a of a to the x equals x. And that's because, again, the loop, a raised to the x would equal a raised to the x. Those are all properties we talked about last time. These next ones are a little bit strange. Let's see, if we have log of any base and you have two things being multiplied together in the log, you can split this into 2 logs. Very important property here. Also, if you have division inside a single log, you can turn that into subtraction between two logs. Then if you have log base anything of x to the n, you can pull the n out in front. This is used so much in calculus. You can pull the power, this power can be pulled out in front of the log. Okay, so you might want to put a star next to that one because that one comes up a lot in calculus. All right. So all of those are properties of logs. I'll just remind you also that since the natural log comes up a lot, right? We use natural log a lot. I'm just going to show you what each of these properties look like with natural logs. So if you do natural log of 1, you should get 0. If you do natural log of e, you should get 1. If you do natural log of e to the x, you should get x. Now, these other properties would be something like this. Natural log of x times y equals natural log x plus natural log y. This property would be natural log of x divided by y equals natural log x minus natural log y. And then the last one would be natural log of x to the n equals n natural log x. All right. Now, I talked a little bit about last time how your calculators really only have to have one key on them. Most calculators either have the natural log key or they have the log key, log key. And so the reason why you only need one key on the calculator is because of this 12th very important formula. It actually is called the change of base formula. We're going to use this extensively today. Well, we'll use it quite a bit. It says this: if you want to take the log of any base of anything, you simply just do natural log of the x divided by natural log of the a. Very important formula. I'm going to show you this in an example, all right? I want to show you this formula by using an example. So for example, last class, we had run into a problem. I'll come back to this page, but we had done this problem where we were stuck. Where is that sucker? There it was. Remember we were stuck right here? We were trying to figure out what this was right here. So we said, all right, what is log base 3 of 5? And so we said, all right, well, one way we can think about this is if we call the other side of this, let's say x, we're trying to figure out what x is. And then if we use the loop, we turn it into 3 raised to the x equals 5. Everyone comfortable with that idea? We're just doing the little loop here. 3 raised to the x is equal to 5. And then we have to figure out what the x is. And we said we couldn't do this because we couldn't get the 3 and the 5 to have like the same base, right? So we were stuck. Well, now if you look back at the original problem, this right here, this looks like this, right? Where x would be what and a would be what? X is 5 and a is 3. So according to this formula, this is just the natural log of 5 divided by the natural log of 3, which we would use our calculators for because our calculators have the natural log key. So please try this on your calculator. Take the natural log of 5 and divide that by the natural log of 3. Someone want to tell me what they get? 1.465. So we'll have to round, okay? Approximately 1.465. How far we round, okay, how far we round is really going to be dependent upon what we're trying to do. When I make the video for the class we're not going to have on Wednesday, we're going to have to make sure that we go out pretty far in our decimals because it'll have a huge impact on our answer if we round too soon. So if I'm just asking you to do something like this, 2-3 decimal places is fine. But for the application problems, we're going to want to go further. And I'll make sure that I stress that when it's time. All right. All right. So so look at what we're saying here is that if you take this 1.465, you raise 3 to that power, you should get something close to 5. It'll be off a little bit because of rounding, but we've got a way of getting this answer now. So we can basically do this for any log now. So it's like we won't get stuck anymore, right? Because of this nice formula. All right. So other than that, there's nothing new. I mean, this is just, we just need to know all these formulas exist, right? And we can use them. And now what we want to do is we want to try solving logarithmic and exponential equations. And you're going to see that they kind of start off nice and they start getting harder and harder and harder and harder. So I just pulled this. This is the homework assignment. There's 40 something problems here. And then another, well, there's 72 total starting at number 5. So there's a lot of problems, right? Of course, I'm not going to ask you to do all of these, but what I'm going to do right now is I'm going to start working through the even ones. And they're just going to progressively get harder and harder and harder. But each one of these is going to have a slightly different kind of approach. So let me start with the first one, log x plus 6 equals 1. Start with that one. This is number 6. So number 6, we want to solve, all of these say solve, okay? Solve log base 6 of x plus 1 equals, I forgot what it said. X plus 6 equals 1, sorry. No, I'm totally messed up. Log x plus 6 equals 1. All right, so we want to solve for x. I want to know what x makes this true. So whenever you see x inside the log, if x is inside the log, what you want to try and do is do the loop, okay? So I'm going to do the loop here. What is the base of this log? 10, right? Because it's not written. So I have to understand that there's a 10 here, and then I go ahead and use the loop. 10 raised to the first power must equal x plus 6. Does that all make sense? We've done ones like this before, so there's nothing really new here. 10 to the first power is 10. So all we have to do is subtract 6 on both sides. And we get over here x, and over here we get 10 minus 6 is 4, and this is our answer. Okay? Now, with log equations, I recommend that you check your answer. And what I mean by check your answer is just make sure that this can be plugged into the log. Because remember, when we were talking about logarithmic functions, we said you cannot plug 0 into a log, and you cannot plug a negative number into a log. So just real quick, if I plug 4 in right here, 4 plus 6, I get 10, right? And so as soon as I see it's 10, I'm like, okay, this is going to work, all right? Because the solution should work. I just want to make sure I don't plug in and get a negative number in there. All right, that one, I bet you just want your next test to just have a bunch of those, right? By the way, your next test is next Wednesday. That's the plan. So I will hopefully get you a review for that by the end of the week. All right. All right, next one. Let's see. Does 8 look much different? 8 doesn't look much different, but we can do it. So where do you see the x? Inside that log, right? It's in the argument of the log. Remember me using that word argument? It's the thing inside the function. So I'm going to go, since the x is in the log, I'm going to loop this up. I'm going to make a 3 squared equals 3x plus 1, or sorry, 3x minus 1. And 3 squared is 9. Be careful, it's not 6, right? We're not multiplying, it's squaring the 3. And now this is just a linear equation, right? I mean, college algebra students should be able to solve this. Add 1 to both sides, divide by 3, and I'll leave it as a fraction. 10/3 is x. And we can check by plugging in. If you plug 10/3 in here for x, 3 times 10/3 should give you 10. And then you take away 1, that should be a positive number, so we should be good. This all good? Amanda? Yeah. All right. Oh, okay. So 10 is different, right? 10 is different. This is This is not the same as what we've had, right? What's the big difference here? Both sides have logs, right? Both sides have logs. Okay, well, you know what? I just realized I forgot to put this property on your properties. Hold on. Right here, I did it for property 3. I did it for exponentials. I forgot to do it for logs. I'll make it formula property 13 up here. Sorry, I apologize. It's if you have log base a of x equals log base a of y. So we just say if this is the case, then what do you think is true? X must be y. So that is another property of logs, that if you have 2 logs, right? They have the same base, but they inside them is different, right? Then in order for that to be equal, the insides have to be equal. So according to formula 13 here, right? So according to formula 13, I know that what's in here, that I can call my x, and what's in this log is y. According to formula 13, I can go straight to this equation. 2x plus 3 must equal 3. You understand what I'm doing there? Just setting the inside of the logs together. Now, I can only do this because they have the same base, right? They have the same base here. If one of these was log base 5 and the other one was log base 3, you can't do it, all right? And we would have a way of doing it. I'm not ready to do something like that yet, but that's why we can use the property. And then here, what happens? Solve this. Yeah, you get 2x equals 0 when you subtract 3 on both sides. You divide both sides by 2, you get 0. And I'll just check my answer real quick. If I let x be 0, I get 3 in here. And so log base 5 of 3, yeah, that equals log base 5 of 3, right? So no loop. I didn't use a loop here. All right, next one. 12. This one's interesting. Where's the x? Inside, right? Inside. So we've got the x inside. We don't have a log on the other side, so we should be able to do the loop here, right? This loop. Now watch when I do this loop. 2 raised to the 4th power must equal the absolute value of x minus 7. And 2 raised to the 4th is 2 times 2 times 2 times 2, 16. 16 must equal the absolute value of x minus 7. So this brings up a question we really haven't answered in this class, is how do you solve an absolute value equation? How do I solve that? Can I just throw away the absolute value, or do I have to do something? So let me show you by kind of doing a separate problem that I think is a little easier. If I tell you the absolute value of some number x equals, let's say 5, then what can x be? 5 or negative 5, right? 5 or negative 5 would work here. So anytime we have an absolute value equation or an absolute value equation like this, what we can do is we can break this down into 2 different cases. We say, okay, well then x must equal 5 or x must equal negative 5. In other words, you can drop the absolute value as long as you look at the cases where you get this side to be both positive or negative. All right, let me see if I can make that make sense to what I'm about to do over here. So over here, I'm going to take this. I'm going to say, okay, this can break down. I'm going to write it this way. To say that this has to be equal to 16 means whatever's in here, right, has to be a 16 or a negative 16, right? Either one of those. So let's do that. We take the 2 cases. The x minus 7 must turn out to be a 16, or the x minus 7 must turn out to be negative 16. So we have 2 equations, and you can solve each one by adding 7 to both sides. So x must be, what do we get there? 23. And then x must be negative, yeah, you're adding 7 to both sides, so negative 9. So these are your 2 potential solutions. So how would we check? We plug 23 in there, right? 23 take away 7 is 16, right? Absolute value of 16 is 16. So what it would become if we plug 23 in is log base 2 of 16 equals 4. Is that true? Is this true? Yes, because 2 raised to the 4th equals 16, right? So that is true. What happens if I plug in negative 9? Negative 9 minus 7 is, I'm sorry, negative 9 minus 7 is negative 16, but then you take the absolute value, don't you? And then that gives you this again. So you get the same answer. So when you look at this, don't throw the negative answer away. A lot of students will be like, oh, you can't plug a negative into a log. Yes, you can plug a negative into a log, but it can't be the final argument in there can't be negative. So everything we have here cannot turn out to be negative. Negative 9 can be a solution, but all of it together cannot be a negative number. That's why we have to check them. Does that make sense? Okay. Here we go. Next one. What was that? That was 12, right? Ooh, this one, again, it doesn't look, well, it looks ugly, but let's see. How do you do this? How do you do that? Well, do you see logs on both sides? You see that they both have same base? Okay, well, if they both have same base, then the arguments have to be equal, right? So that means that the absolute value of 3x plus 4 must equal the absolute value of 5x minus 12. How in the world do we solve that? Right, because I just gave you this example. If we had absolute value of x equals 5, I told you that breaks down to be x must equal 5, right? And x must equal negative 5, yes? But see here, both sides are absolute values, right? Both sides are absolute values. So let's try using the same idea. If the 5 is like this is, right, all of that, just imagine the 5 here is like this, then this would break down to 2 equations. What would those 2 equations be? 3x plus 4 must equal everything though, right? It would be the whole thing, right? Because that's the right side of the equation. So I've got to have whatever's in the absolute value here, x, must be equal to that number or the negative of that number. So I'm going to say it must be equal to the absolute value of 5x minus 12, or the 3x plus 4 must equal what? The negative of the absolute value of 5x minus 12. Do you all see that? The absolute value of 5x minus 12 is like the 5 over here. We good? Now, each of these are new absolute value equations, aren't they? So you can do the same thing we just did. This is going to break down to 2, and this is going to break down to 2. Understand? Now, I think on this one right here, before I break this into 2, I'm going to multiply both sides by -1. So I'm going to go negative 3x minus 4 must equal the absolute value of 5x minus 12. Now I'm ready for that to break down into 2. Over here, I'm happy with this because it doesn't have a negative here. So I'm ready to break that one down into 2. So when we do this first, we're going to I'll put the 5x minus 12 must equal just this side, right? 3x plus 4. Yeah. Or the other equation is the 5x minus 12 must equal what? Not 3x plus 4, but negative of the whole thing, right? So negative 3x minus 4. I'm out of room there. Everyone at home understand that? Any questions there? This doesn't come up a lot where you have 2 absolute values in the same equation. So we need to make sure we understand how to do it. You all right at home?
Yes, sir.
Okay. What about this one? Same idea, right? We're going to do the 5x minus 12 equal to this, and then 5x minus 12 equal to the negative of that. So 5x minus 12 equal to the negative 3x minus 4, or the other equation is 5x minus 12 equals the negative of this, which is 3x plus 4. Just changes the signs, right? Are any of these equations the same? Yeah, look at, they're the same, right? Like they're in pairs, aren't they? Like this one is the same as this one, right? And this one is the same as that one. So we really only have two equations to solve here. The reason I'm showing you this is because later on in other math classes, you might run into this again. And the safest bet, especially if this is an inequality, is to set up, break it into two and then break each one of those into two. And if you've got some that match, great. If you don't, just, work each one. So I'm going to just throw this one away and that one away, and I'm just going to go back to this one and solve these for x. So on this first one, I'm going to just subtract 3x from both sides. And I'm going to add 12 to both sides. So I should get 2x is 16. That gives me a solution of 8. And then on this one, I'm going to add 3x to both sides. So I get 8x. And I'm going to add 12 to both sides. So I should get 8. So you should get x is 1. Is that all right? We can check our answers, 8 and 1, by going to the original problem and plugging 8 in here. 3 times 8, right? 24 plus 4, 28, and then 3 times 8, 40, and then take away 12, 28, right? So it works. And then you can try 1. If you plug 1 in here, you get 7. Oh, wait a minute. If you plug 1 in here, what do you get? -7, but it's the absolute value, right? So it turns it back into a +7. Okay. We move on. 16. Where's the x? Inside of a log, right? We got logs on both sides. Do they have the same base? Yes. Can we just set x equal to 9? Why not? There's a -2 in front of that other log, right? See that -2? That causes a problem. What can I do? Yeah, so if you try and divide both sides, like a lot of people say, oh, let me just divide both sides by -2, right? I'll just divide both sides by -2. The problem is it'll get rid of the -2 on this side, but now you'll have a fraction on this side, and you still can't use the property 13. So what we're going to do is we're going to use property 11, the big one. This property says that if you have a power on the x in a log, you can pull the power out, and it becomes a number in front of the log. Well, we're going to use this property backwards. We're going to take the number that's here and we're going to push it up as a power. So I'm going to take this -2 and I'm going to push it up as the power on that x. So now I have log base 4 of x to the -2 equals log base 4 of 9. Now I can use property 13. So this is property 11 I just used. Right? And now property 13, which is the fact I can set the insides equal to one another. X to -2 equals 9. X to -2 equals 9. Well, here we have to continue to solve this. This is not x squared, it's x to -2. So I'm going to rewrite that as 1 over x squared using just properties of exponents, right? You have a negative power, drop it down. I'm going to multiply both sides by x squared. I'll get a 1 on the left side. So I'm clearing fractions here, right? Getting rid of the fraction. And I get 9x squared. Getting closer. Divide by 9. And then finally take the square root. When I take the square root, I'm going to have to do what? Plus or minus, because I brought the square root in, right? I'm the one who did it, so I need plus or minus. And so when we do that, we get plus or minus. We can take the square root of the top and bottom separately, 1/3. We have two answers, positive 1/3 and negative 1/3. We should check. There could be an issue here. We'll have to just make sure that we don't have an issue. Let me go back up to the original problem. -2 log base 4 of x equals log base 4 of 9. Can I plug 1/3 in here? Yes, because I can plug 1/3 in here and I have a positive number inside of a log. Can I plug negative 1/3 in? No, I cannot. I cannot plug negative 1/3 in. So I only have one answer. Do you understand? Because you can't plug negative into a log. Okay, so got to throw out one of these answers and only take the positive answer. X equals 1/3. All right, next one. I'm trying to go through these because there's so much variety in these problems that I want to make sure that I'm covering everything that you'd run into. 18. What do you see here that's different on 18? There's numbers on both, right? Now we do have two logs, so we can set the insides equal to each other, but we've got to have that 2 and that 3 out of there. Well, that's okay. We can push them up as powers, right? So using property 11, or sorry, property 11. Yeah, property 11 first. We push the 2 up as an x squared, and we push the 3 up as a 4 to the 3rd power. Okay, so that's your property 11 right there. Now your property 13 says you can push these together, or not, sorry, not push them together. You can set the insides equal to one another. 4 cubed, 64. And then you take the square root on both sides. You get plus or minus 8, right? The square root of 64. Check your answers, right? You can plug 8 in there. You can't plug negative 8 in. So just 8. I'm just curious, why can't I plug 8 in, negative 8 in there? Because look, just look at that log, right? This is x. I'm telling you, I can't plug negative 8 in there. Why isn't anybody arguing with me saying, well, wait a minute, if this is equal to this, then you could plug negative 8 in, right? Do you all agree I could plug negative 8 in here? Yes, right? And I can't plug negative 8 in here because it's not squared, right? But this isn't doesn't the property say I'm allowed to move that 2 up here? So why is it not okay to plug in here, but it is okay to plug in here? It has to do with the way the expression is presented to you in the beginning. When you check for the domain, what you're allowed to plug in, you have to be looking at the way the equation was presented. You cannot do any algebra to it and then talk about the domain or what you can or can't plug in. I'll give you an example. We've talked about this before with rational functions. If I give you these two functions, f of x equals x over x versus this other function, g of x equals 1, these functions are essentially the same functions. If I plug a number into this, like 3, I get 3 over 3, that's 1. If I plug in 5, 5 over 5 is 1. Any number over itself will be 1. So they're exactly the same functions, except where? At what number? At 0, right? I cannot plug 0 into this. I can plug 0 into this. So the difference between these is very minimal. It's that you can't plug 0 in. to the f function. Now, if you were to come in here and algebraically simplify that, cancel the x's and make that a 1, you've made a mistake. Now, if you do that, you think that you can plug 0 in, right? Because you're looking at this one. When you canceled, you were promising me x couldn't be 0. You had to make that promise to me to make that cancellation. That's kind of like what this is saying. It's like, okay, you're allowed to bring that 2 up here as long as you promised me that that wasn't a negative number to begin with. If it was negative to begin with, then you can't do this property. Understand? Same sort of thing. All right, 20. I know this looks like this huge, like we're going to be here for a while. I understand, but there's so much variety in these. Let me see. The next one, yeah, we need to do it. Why don't I give you a second or so, a minute? See, let me give you like 30 seconds to see if you can at least see how to start this. We have not had one like this before. We've got 2 logs, but they're on the same side of the equation. On the other side of the equation, we have a 2. Whoa. That's a good problem. I'm only going to give you like 30 seconds to think about it. So like everything else in algebra, as long as you don't break any rules, there's a lot of different options as to how to go about something. So I'm curious, just does anyone have anything that they started with? And okay, so you took that 2 in front of that first log and you pushed it up as a power. Does everyone agree that we could do that? I agree. Let's do it. There's nothing wrong with that. We're not breaking any rules. So log base 3, it was the x plus 4. That's all going to be squared minus log base 3 of 9 equals 2. All right, I'm okay with that. Right here, property 10, if you ever have 2 logs with subtraction between them and you have the same base, a, and they have different arguments, whatever's in them, you can put those together into a single log with division. All right, I'm okay with that. I mean, that's a property, right? Could I have done that before the 2 got pushed? No, I could not do it before the 2 gets pushed up, because this property says if you have there's like a hidden 1 here. There's a 1 in front of that log, a 1 in front of that log. You cannot use this property if there was a 2 in front of one of these. So we had to push that 2 up first. So now the left side is going to condense down to a single log, and it's going to be inside that log division. It's going to be x plus 4 squared over 9, then equals on this side 2. All right with that? I'm on board with this. What now, though? That was property what, 10? That was 10, number 10 in our properties. Yeah, the loop, right? Let's just do the loop now. See, we have a single log on the left, we have a number on the right. So let's just loop it up. Go here to there equals that. So 3 squared equals x plus 4 squared over 9. That's just the loop property of the log. It's kind of the definition of a log. Now 3 squared I know is 9. So the left side's 9 equals x plus 4 squared over 9. What can I do now? Yeah, let's just clear out that fraction. Let's multiply both sides of the equation by 9. And we should get them continue up here. We should get 81 on the left side equals x plus 4 squared. All right. We're getting close here. Let's get rid of that squared. Let's do square root on both sides. When we do that, we will have two answers on the left. Plus or minus 9 equals the x plus 4. So I've applied the square root on both sides, making sure to do plus or minus. One last step to get that x by itself. Just take away 4, right? On both sides. We have two answers. We have positive 9 take away 4. That's 5. And we have negative 9 take away 4. That's negative 13. Understand, everyone? We have to check these answers. And where do we have to check them? The original one, right? So can we plug 5 in here? Yeah, 5 plus 4 is 9. We should be good. Negative 13? No. Chunk it. But please be careful on test. Don't tell me you're throwing out negative 13 because it's negative down here. You're throwing out negative 13 because when you plug it in, you still get a negative number. That's why you're throwing it out. All right. Did anyone do it a different way? There's nothing wrong with what we did. All right. Can somebody tell me what this is? What number? Huh? No. What is this telling? What is this asking you? When someone writes log base 3 of 9, what are they saying? They're saying 3 to what power is 9? That's what that means, right? 3 to what power is 9, which is
2.
Right? So wasn't this really just 2 log base 3 x plus 4? It was minus 2 equals 2. Wasn't that really what that was? And then can I add 2 to both sides? And get 2 log base 3 of x plus 4 equals 4, right? And then divide both sides by 2. Now if I divide both sides by 2, I will get log base 3 of x plus 4 equals what? 2. And did we have that? No, we didn't have that anywhere. Let me continue this. Sorry, I'm out of room. I'm gonna have to do it up here. So we get log base 3 of x plus 4 equals 2. And now I can do the loop, right? I do the loop, I get 9 equals x plus 4 and subtract 4 on both sides and I get 5. Do you notice that by doing it this way, we didn't get this solution? So when we do a problem, and this goes for any math class you're ever taking, if you're ever solving an equation and you get a group of solutions where some of them work and some of them don't, the ones that don't, these are called extraneous solutions. By doing our algebra a slightly different way, we got the answer without that extraneous solution. The good news is as long as you do your algebra right, if there's a real answer, it will be there, right? But depending on your algebra, you might get extraneous solutions mixed in, which is why we have to check them. All right. I actually didn't see that until we were like right here. And I was like, oh, wait a minute, hold on. We could have done it a little differently. It's all right. That was a good exercise. So how about 22? This seems like a grind. Does this seem like a grind? I hope that this is worth going through all these different types because, okay, good. All right, so I'm looking at that. I'm seeing 2 logs on the left. I'm seeing just the number 2 on the right. So this is not like the last problem because like that log base 3 of 9, we could turn it into 2. Nothing here, right? Both the logs have x's in them. Now, neither one of them has a number in front, right? So I don't have to worry about pushing a number up. But I really am trying to get myself to go to the loop. I would like to use the loop here, but the loop only works if you have a single log. So can we push those logs together? Yes. What property is that? Let's see. What property turned, yeah, it was 9. We could take 2 logs being added and compress them down into a single log. Let me show you something while we're talking about this. My Cal 2 class today, here's a problem. In my Cal 2 class this morning, we were working on a problem. And where is it? Right here, this problem right here. This was the problem we were trying to do. And we tried doing something. And then the first step we did, the first step was we used that property 9 or property 10 that you're looking at right there backwards. We said we had a natural log and we had division in here, and we turned it into 2 natural logs with subtraction. That's the first thing we did. And then we just continued and worked out the problem. But I'm just showing you these little things, these little properties, they just kind of peek their heads out all over the place in different classes. So we just want to be kind of comfortable with them. Well, kind of comfortable, very comfortable. All right, so I'm going to put those together, and you said this was property 9. So number 9, and when we push those together, we get a single log, and inside the log, we get the 2 things that were in those logs multiplied. So x times x minus 21, and then equals 2. Got it? Now what? The loop, right? The loop, because we have a single log equals a number. What's the base? 10. Okay, so this is what? 20 equals x? No, not 20. What is it? 100, right? Make sure you're squaring it, not multiplying it. Oops, 21. And now we look at that equation and we say, hey, that's quadratic. Multiply the x through, right? You get 100 equals x squared minus 21x. How do we solve quadratics? Move everything to one side. So I'm going to set this equal to 0 by moving the 100 to the other side. And now we can either factor this or use quadratic formula. I think factoring is going to be the way to go here, right? Does factor? 25 and 4 should work if we get the signs right. I was going to mention that, and I didn't mention it on purpose because I thought that maybe I had mentioned it before, but I'm so glad that you asked. Let me finish this and then I will address your question, because it's a really good question. So here I'm going to factor, right? I'm going to get minus 25 and plus 4. Y'all agree? Those 2 numbers multiply to be negative 100, add up to be negative 21. Set each of those equal to 0. You should get 2 answers, positive 25 and negative 4. Now, I'm not going to throw that negative 4 away because it's negative. I'm going to check both of them, all right? So go back up to the original. Can I plug 25 in? 25 in here? Sure. 25 take away 21? Yes, right? It's a positive number. So 25 will work. Negative 4 won't, because when I plug it in there, I get a negative. So I got to chunk it. Yes, I do have to throw it away. So we only have one answer, 25. Any questions? Now, the question that was brought up here in class is this. When we have this equation, can we just set the x equal to 100, do 2 equations here, and then set the x minus 21 equal to 100? Is that what you're asking? What do y'all think? Can we? Why? So what now? Say again. Okay, so this is such an important thing. If I tell you right now that I have let me do it this way. If I say x times x minus 21 equals 0, okay, think about that equation. We would do this by setting each one equal to 0, right? X minus 21 equals 0. Right? And then each of those, you get 2 answers, 0 and 21. And look, if you plug in 0, you get 0. And if you plug in 21, you get 0, right? That only works if this side of the equation is 0. If it's another number, it's not necessarily true. I can give you an example. If I tell you right now that two numbers, x times y equal 0, all right, then one of these has to be 0. One of them has to be. So either x is 0 or y is 0. But if I tell you that two numbers multiply to be equal to, let's say, 5, that does not mean that one of these has to be 5. Now, could one of these be 5? Yes, but do they have to be? No, right? I can give you an example right now of two numbers that multiply to be 5 that neither one of them is 5. How about 25 times 1/5? Those two numbers multiply to be 5, but neither one of them is 5. So if you set x equal to 5 and y equal to 5, you're going to miss answers, right? That's kind of what's happening here. Because we have two things being multiplied together to be 100, if you set them each equal to 100, that's not good enough. You're missing all these infinite number of answers. So the only way to do this is to move the 100 over and then solve. Good question. This is actually called the zero factor property. Basically says that if you have two things, a times b, that equals 0, then a equals 0 or b equals 0. But it's called the zero factor property. The key word here being 0, meaning the right side has to be 0 for this to be true. If it's something else, well, then it doesn't work. All right, that one was kind of cool. What was that one? Number 22? 24. These are starting to look similar now. Let me see. Let's do 24, because I think if we do 24, that'll pretty much cover us till we start getting down here. So let me do 24. Two logs, right? Two logs. Neither one of them is easy to convert over. Like we don't have log base 3 of 9 or something like that that just turns into a number. I'd like to get this into a single log. If I can get it to a single log, then I can do my loop. So I have subtraction between the two. Subtraction between two logs turns into a single log with division. And when I don't shave, my stubble tears up the inside of these things and just starts tickling me. Okay, what's the base? I'm about to go loop on us, right? Base is 10, so 10 to the 1 is 10 equals 2x over x minus 3. This is a rational equation, and we have a method for solving rational equations. We clear fractions, right? So we multiply both sides by x minus 3. That'll clear out the right side, give us a 2x. Over here, we have to distribute 10 through, 10x minus 30. And then just rearrange things. Move your x's to the left, 30 to the right, divide by 8, reduce, 15 over 4. Check it. 15 over 4. If we plug it in here, 2 times 15 over 4, it's still positive. 15 over 4 minus 3. Let's see, 15 divided by 4. That's bigger than 3, right? It's bigger than 3, so we're good. Okay. All right. Looking good, looking good. Let's just talk about the next few. That was 24, right? 26. Tell me what I would do here. Put them together first, right? And when we put them together, you're going to multiply the two insides together, aren't you? That's going to be a quadratic, isn't it? And now you're going to do a loop, but your loop's going to be 6 to the 1, right, equals that quadratic. So then you'll have a quadratic equals 6 to the 1, move everything to one side and factor quadratic formula, right? 28. Trying to trick you here. Yeah, let's move all the logs to the left, right? Take this log, move it to the left. So make it a plus it on this side, plus it on this side. And then won't it look like 26 again? Right? Because you have two logs on the left side, both of them added together, condense those down into one. It'll be a quadratic, and then do your loop again. Make sense? Okay, how about 30? Yeah, so look at 30. You have two logs being subtracted, right? We can turn this into division in one log. Yeah, let's do that one. Just because there's only one little subtle difference on this one, and it's just the base, right? So let's take a look at it. So if we do this, we're going to condense the left side down into one log. So natural log, and then we'll have x plus 1 on top, and x on the bottom equals 2. Okay. That makes sense, that step? Now the loop. Nope, natural log has a different base. LOG has base 10. Natural log is base what? E. It's base E. This is the first time we've seen this. So this is really like E. So this is going to be E squared equals x plus 1 over x, right? Now, E squared, we should probably just use our calculator, and we're going to get a decimal answer here. So we're going to approximate it by doing E squared is about 7.389, roughly, is approximately equal to x over x, x plus 1 over x. And now what? You have a rational equation. Multiply both sides by x. So clear those fractions out. Hit both sides with an x. So now you'll have 7.389x equals x plus 1. Then subtract 1x from both sides. Good. For those of you who are at home, I don't know if you can hear, I'm getting responses from the class. So that's why I ask and then I immediately say the answer. So I know when you watch it back on video, it just sounds like I'm asking and not even giving anyone an opportunity to answer. Okay, so now divide by 6.389 on both sides. So 1 divided by 6.389 is approximately 0.157, approximately. I should check it though, right? I should check that answer. So if I go back to the original one, this is a positive number, right? 0.157 is positive. If I plug it in here, 0.57 plus 1 is still positive. And if I plug 0.57 in here, that's good too. So the difference on that one was just the fact that we had a base of E. Otherwise, we're still using those properties. All right, let's look at 32. Any differences on number 32 that you can see? Anything that looks different or out of place here? Not really, right? You would just put those together with the addition, right? Squeeze these two together, you'd have a quadratic, right? You do your loop, 2 to the third, that's 8. You should be able to work that out. How about 34? This subtraction will turn these two logs into division, right? The only thing that's going to be weird is you're going to have x squared minus 9 over x plus 3, right? Equals, you know what? Why don't you try this one on your own? I'm going to step out for just a second. Try number 34. Because I think there's a way you can make 34 harder than it has to be. If you don't do some factoring first. I'll be right back. Today is about exponential and log equations. All we've done are logs. We still have exponentials to talk about. Yeah. So the danger here comes if you try and clear those fractions before you simplify. Right, so first step is to turn it into a single log with x squared minus 9 over x plus 3 equals 3. And then when you do your loop, 4 to the third equals x squared minus 9 over x plus 3. Here, you may want to like multiply both sides by x plus 3. If you do that, though, your numerator, well, it's just going to get more complicated than it has to be. It's better, I think, if you just see, what is 4 cubed? 64, okay. It's better if you just see that the right side factors the top. And then they're gone like that. And then you just have a nice little linear equation. 64 equals x minus 3. You still could have got it the other way. It's just a little bit messier. 67 is x. And then you could just check your answer, plug 67 in. 67 squared minus 9 is definitely a positive number. 67 plus 3, yeah, should work. Questions? That was 34, right? Okay, how about 36? 3 logs. And then wait, and then move it to the left and then put those together. Is that what you said? Okay, let me see. Let me see if I notice on this one that look at the base. What's the base? A. It's not a number, right? It's just some number we don't know. So I'm being told here, put those together first. Single log inside multiply, right? X times x minus 2 equals log base A x plus 4. I agree. Now you could move that log to the other side and do subtraction turns into division. But why don't we use the property that you can just set these two equal to one another right now because you have the same log, same base on both sides. Set the guts of that together. X times x minus 2 equals x plus 4. That's that property 13. Set the insides equal to one another. And this is a quadratic, isn't it? X squared minus 2x equals x plus 4. Move everything to one side. So subtract x on both sides, subtract 4 on both sides. Factor. 2 solutions. 2 potential solutions, right? 4 and -1. Set each factor equal to 0. We must check. Are there questions on these steps? So to check them, got to go all the way back up here. 4 goes good here, 4 goes good here, 4 goes good here. -1 can't go in here. Can't go in there or here. You could plug -1 to this one, right? But just not these two. So got to throw that one out. I know it looks like no negative answers ever work. I know it looks like that, but you have to check them because it is possible. All right. Any of these look weird? I think 40 looks, I think these last ones are worth us talking about. They just look massively nasty. Okay, you have 4 logs. All right, big deal. They're all the same base, yes? 3, 3, 3, 3 on all of them. So we can use properties. We can blend them together if we want. So any ideas here? Do what? Okay, so push those numbers in front up. So I'm being told here to take this 2 and push it up and the 2 here and push it up and leave the negative. Is that what you're saying? Leave the negative. So just make that a +2 up here and then a +2 up here. Good? You all right with that? All right, let's do that. So we have log base 3 of x minus log base 3 of what? 5 squared, 25. equals log base 3 of x plus 1 minus log base 3 of 100. Okay. Now what? You want to put, okay, so you want to condense that left side together using a property that allows you to turn subtraction between two logs to division. That's fine with me. That'll become a single log, base 3, it'll become x over 25, right? The other side will become a single log. I'm guessing this is what you want to do here too, right? Push the other two together on the right, become x plus 1 over 100. Now equal the arguments together, right? Equal those up because we have log 3, insides must be equal. X over 25 equals x plus 1 over 100. How do you solve that? Multiply by 100. You could cross multiply if you like that idea. I mean, however you want to do it. Most students like the idea of cross multiply. So I'll do that. I'm going to multiply the 100 here times the x, and then multiply 25 over here. Just make sure that 25 has to distribute to both terms. That's linear, right? Subtract 25x and divide by 75. 1/3. 25 over 75, right? Check our answer, right? 1/3. Yep, we can plug 1/3 there. We can plug 1/3 there. 1/3 plus 1 is positive. These other logs don't have x's in them. Now, is this the only way to do this problem? Probably not. You know, you could have maybe moved this whole log to the right and moved this log here to the left. And I mean, there are different ways to go about it, but I think this worked out fine. 40 looks real weird. Thoughts? You want to take the 3 that's outside there and distribute through the parenthesis? No? Oh, you want to do what's in here first? Okay, you you want to put those together? Yeah, we could do that. You want to do that? Now, another thing I could do is distribute the 3 through, right? Okay, but I'm going to do it this way. I'm going to put these together first. So I have a 3 out here in front. When I put those two logs together, they have the same base, so I can do this. Log base 7 should be x over 2. Like that. Take that x, divide by that 2, and then that equals the other side. What do you want me to do here? Leave it alone or mess with it? Okay, you take log base 7, take 4 squared, so 16. So we took that 2 up on the 4. Now what? Yeah, take the 3 here and push it up here, because the parentheses really don't matter anymore because this is a single log. I can push this 3 up. So it becomes log base 7 of x over 2, that whole thing cubed equals log base 7 of 16. Now what? Yeah, equal the arguments. This is the argument of the first one. That's the argument of the second one. Set those equal to one another. So we should have x over 2 to the third equals 16. Ooh, okay, that's kind of weird. You could do that. You could do x cubed over 2 cubed, right? Cube the top and bottom. Now what? Multiply both sides by 8. So what's that? 8 times 80 and 48. It's like 128. Now? You could do the cube root though, right? You could do the cube root on both sides. Now, when you do cube root, do you have to do plus or minus? Only on evens, only on even roots. So we can leave this as cube root of 128. I don't believe that's a perfect cube. Yeah, so that's our answer. Now we have to check it. This is a positive number, right? Let's see what happens. Yeah, I can plug it in here, right? I can plug it in here. That's a weird answer. Another way. I don't see, I mean, there's other things we could have done. We could have distributed 3 first. All that would have done was made that x cubed and 8, right? And then when you put them together, you would have basically been down here. Another thing you could have done, you could have divided both sides by 2 to start. Like if I divide by 2 here, then this becomes a 3 halves. And then we could move that up as a power, but that'd be weird. That'd be weird to have a 3 halves power, but that algebraically would have been okay. I think the way we did it is probably the cleanest way. Weird answer, but it's the answer. Let me see. Let's do these last 2. I mean, we may as well come this far. All right. So for these, first one, let's ignore this one for now. Do they have the same base, the logs? Yeah. Okay, so. Yeah, take this 1/3 power and why don't we move it up, right? 2 to the 1/3, that's weird, but let's do it. Log x minus 1 equals log 2 to the 1/3 power. That's the same as the cube root. Okay, that 1/3 power means cube root. But these 2 logs have the same base, so I can set their arguments equal to one another. X minus 1 equals the cube root of 2. I don't know what that is, just the cube root of 2, whatever that number is. And just add 1, and I'm done. 1 plus the cube root of 2. That wasn't so bad. Make sense, Amanda? Yeah. I could have also multiplied both sides by 3 in the beginning. 3 here and kill this off. And then move that 3 up as a power. But then I would have got the same thing in the end. I would have got x minus 1 cubed equals 2 when I set the arguments together. And so then I would have done cube root here, and you would have been exactly at the same place. So that one wasn't too bad. Last one. Ooh, tricky. Yeah, good question. Okay, so look at that middle one. Let's just look at this. The square root of natural log of x. The question I think that's being asked here is that the same as natural log of x to the 1/2, where the 1/2 is on the x?
The cube root of log was 103.
It was, so it is 1/2, right? But the question is, if I write this right here, forget the left side. If I write this, is this 1/2 power acting on the x or on the entire expression? Am I taking the square root of the x or the square root of the whole expression? Just the x, right? So our properties of log says that we can take this and we can move the 1/2 down, right? Like this. That's correct. This is correct. I can do that. All right. But the problem is this 1/2 acting on the x is not the same as this. This is actually this. It's the natural log of x, the whole thing to the 1/2. And this log property doesn't work this way. You can't pull this 1/2 out in front because this 1/2 is not acting just on the x, it's acting on the entire log function. So that means that we cannot put this as an x to the 1/2. We can't even put a 1/2 in front of this. We have to leave the square root here. Okay, this is a good problem. I was waiting for one of these to show up. All right. Okay, you ready? Unless anyone has an idea. Isolate the square root. Okay, so you're seeing this is like a square root equation, right? If we isolate the square root, then we can square both sides. Ay, ay, ay. I don't know if I want to do that. Can I push the 3 up? Can I push this 3 up to this x? No, because the root is trapping the log. You cannot push that 3 up here. Okay, so I like the idea of isolating the root and squaring both sides. I like that idea. But I have a different suggestion. Okay, here's my suggestion. I would like for us to make a substitution. Now, the substitution I'm going to make is going to seem unnatural at first, but let me do it. I'm going to make a substitution. I'm going to say, let u be the square root of the natural log of x. Anywhere I see square root of natural log of x, I'm going to replace it with u. Now, just so you see why I'm doing this, what is u squared then? If I ask you to square both sides of this, what do you get? Natural log of x, right? Understand? So by making this substitution, right, this is a substitution, this very kind of awkward substitution, I'm going to rewrite this problem. So the problem is now going to become what? Well, what's natural log of x? U squared, isn't it? So this becomes u squared minus 3 times the square root of natural log of x, which is u, plus 2 equals 0. Right? Doesn't this equation become this? And that's a quadratic in the variable u. So if I can factor that, I can get solutions, which it does factor, right? Minus 2, minus 1. And so I have 2 solutions. U is 2, u is 1, right? But we switched, right? We made a substitution. I'm telling you what u is. We want to know what x is. So now what I need to do is replace my u's with what we said u was, which was the square root of natural log x. So I'm going to replace the left side with square root of natural log x equals 2. And then on the other one, square root of natural log x equals 1. And now I have 2 little log equations to solve. So how about the first one on the left? How can I solve that now? Square both sides, right? If I square both sides, the square root goes away. 2 squared, 4, right? I can do the same thing on the other equation. So square both sides. And 1 squared is still 1. We're almost there. How do you solve for x? Use a loop. Loop it up, right? You want to solve for x. X is in this log. Do the loop. What's the base? E, right? E. LOG is the base 10. Yeah, so this will be e raised to the 4th equals x. And this one is e raised to the 1 equals x. E raised to the 1 is x. E raised to the 4 is x. And now you could get these on your calculator, or you could just leave them like this. Check your answers. Both e to the 4th and e to the 1st are both positive numbers, so they should work in here. All right, so this is probably the cleanest way to see this, to do this, is to see this substitution, which isn't very natural. I don't know, did you go and try and do it the other way where you moved it over and square both sides and stuff? You'll still get the same answer, it's just a little messier. All right, that was worth it. That was worth us doing for sure. All right, let's see. This one is similar to the one we just did because you've got this whole log being squared. That 2 is not on that x. So what you do here is you make a substitution. Do y'all see what the substitution is? Yeah. What is it? Log base 3 of x. Replace log base 3 of x with u, and you'll have a quadratic. Go solve the quadratic, replace the u with log base 3 of x, and you should get it. Okay. We all good? So that's a good variety of log equations. So now I'm debating, do I start exponential now with like 13 minutes left and see how far we get? Because these get pretty messy. Or do I stop here and make this what my video is over? What do y'all think? You like stopping?
I don't like doing too much. I like to hold on to
Yeah, let's stick, because this is going to be different. This is going to be a different method. Well, not different method, but we're solving different types of equations here. I think this is a pretty natural place to stop. So yeah, this is what we'll do, because I think this is probably a good video. Is what I'll do is your homework tonight will be to, like before, work through enough of these to feel comfortable. But after seeing me go through all the evens, I think you can see there's like little subtle differences in the problem. So make sure you don't just do like 5 of those. Try and do as many of those odd ones as you can. And then what I'll do is I'll do a video where I work through the evens on this. And that way you can see the little subtle differences in how you solve these. And I'll make your assignment that'll be collected, and I'll tell you when it's due and stuff, will be for you to turn in these odds, all of them. Okay, so that clear to everyone? This is what I'm going to cover on Wednesday in a video. And then your assignment will be the odds through here. And I will send this, right? I'm going to send this to you all. I'll put it in that folder for you so you can get to these. So tonight, just do those. All right. Any questions? All right. So that's it. We're good. Let's call it a day. If you have any questions, I'll hang out. I'm going to send this to y'all right now. I'm going to export this. Anybody at home have any questions?
No, sir.
Okay. Zoom notes. There we go. There's a PDF. There we go. All right. Check your email again, like I said.